Imagine this. No stars, no galaxies, no atoms, no light, not even time itself, just silence. Now ask yourself the question that has haunted physicists, philosophers, and astronomers for centuries. What existed before the Big Bang? Was there a universe waiting to be born? Or was there truly nothing? Tonight we are going to explore one of the greatest mysteries in science, the moment before everything began. About 13.8 billion years ago, something extraordinary happened. In a moment smaller than a fraction of a second, the entire universe exploded into existence. This event is known as the Big Bang Theory. But here's the astonishing part. The Big Bang was not an explosion in space. It was an explosion of space itself. Every galaxy, every star, every planet you see today began as an infinitely dense point called a singularity, a point smaller than an atom, yet containing all the energy of the universe. But this raises a deeper question. If the Big Bang was the beginning of the universe, what existed before it? Here's where things become strange. In modern physics, time itself began with the Big Bang. According to Stephen Hawking, asking what happened before the Big Bang might be like asking, what is north of the North Pole? It simply doesn't exist. Time and space were born together in the Big Bang, meaning there may have been no before. Imagine trying to watch a movie before the first frame exists. You can't, because the story hasn't started yet. But some scientists believe the story may go back further than we think. One possibility comes from quantum physics. According to the strange laws of the quantum world, empty space is never truly empty. Even a vacuum is filled with tiny fluctuations of energy, particles appearing and disappearing. Scientists call this the quantum vacuum. Some physicists believe our entire universe may have emerged from one of these quantum fluctuations. In other words, the universe may have appeared from nothing, but not the kind of nothing we imagine. A quantum nothing, a restless ocean of energy waiting to create reality. Another possibility is even more mind-bending. Our universe might not be the only one. Some scientists believe the universe may not have begun at all. Instead, it might go through endless cycles of expansion and collapse. This idea is called the Big Bounce. According to this theory, a previous universe collapsed under its own gravity, shrinking smaller and smaller, until it reached an unimaginable density. Then suddenly it rebounded, creating the Big Bang. If this is true, our universe might be one chapter in an endless cosmic cycle. There may have been countless universes before ours. According to the multiverse theory, there could be countless universes constantly forming, each with different laws of physics, different stars, different realities. In this view, the Big Bang was not the beginning of everything. It was simply the birth of our universe within a much larger cosmic system, like a bubble forming in an infinite cosmic ocean. Some scientists believe the universe may not have begun at all. Instead, it might go through endless cycles of expansion and collapse. This idea is called the Big Bounce. According to this theory, a previous universe collapsed under its own gravity, shrinking smaller and smaller, until it reached an unimaginable density. Then suddenly it rebounded, creating the Big Bang. If this is true, our universe might be one chapter in an endless cosmic cycle. There may have been countless universes before ours, despite our most advanced telescopes, our most powerful mathematics, and the brilliance of generations of scientists. We still do not know what existed before the Big Bang. The earliest light we can observe is called the cosmic microwave background. It is the faint echo of the universe when it was only 380,000 years old. But beyond that point, the universe becomes opaque, a wall in time. Everything before it remains hidden. For now, look up at the night sky. Every star you see, every galaxy billions of light years away, every atom in your body was born from that single moment. The Big Bang did not just create the universe. It created time, space, matter, and possibility. And perhaps the most astonishing part is this: the universe evolved for 13.8 billion years, so that you could exist long enough to ask this question: what came before the beginning? And somewhere in the future, humanity may finally discover the answer. Until then, the moment before the Big Bang remains one of the greatest mysteries of the cosmos. Right after the universe was born, something unbelievable happened. In less than a trillionth of a second, the universe expanded faster than the speed of light. This event is known as cosmic inflation. Imagine a balloon suddenly inflating from the size of an atom to the size of a galaxy. That is how violently space expanded in the first instant. Before inflation, the universe was unbelievably tiny. After inflation, it had already become enormous. This rapid expansion smoothed the universe and planted the seeds of galaxies. Tiny fluctuations in energy eventually became stars, galaxies, clusters of galaxies, and ultimately us. But where did the energy for this cosmic inflation come from? Some scientists believe it came from a mysterious field known as the inflaton field, a force that briefly dominated the newborn universe. Yet the deeper question still remains: where did that field come from? Now imagine something even more astonishing. What if our universe is not the only one? Some cosmologists believe inflation never truly stopped. Instead, it may still be happening somewhere beyond our observable universe. This idea leads to the theory of the multiverse. In this model, universes form like bubbles in an endless cosmic ocean. Each bubble is a universe with its own laws of physics. Some universes might contain more dimensions. Some might collapse instantly. Some might never form stars at all. And in an infinite cosmic landscape, our universe might simply be one bubble among countless others. If this is true, the Big Bang was not the beginning of everything. It was merely the birth of our local universe. Another possibility suggests the universe may not have had a beginning at all. Instead, it might go through endless cycles of birth and rebirth. Scientists call this the Big Bounce theory. In this scenario, the universe expands for billions of years. Galaxies drift apart. Stars slowly die. Eventually, gravity begins pulling everything back together. The universe collapses. Smaller, hotter, denser, until once again it reaches a point similar to the Big Bang. Then suddenly it bounces, creating a brand new universe. If this theory is correct, there may have been countless universes before ours, each one living and dying in an eternal cosmic rhythm. But our universe may be stranger still. Some physicists believe reality contains more dimensions than we can see. According to string theory, the universe may contain up to 10 or even 11 dimensions. We only experience 3 dimensions of space and 1 of time. But hidden beyond our perception could be extra dimensions curled up at incredibly tiny scales. These dimensions may influence gravity, particle physics, and even the birth of universes. Some scientists believe the Big Bang may have been triggered by the collision of higher dimensional universes. Imagine 2 enormous cosmic membranes colliding in a higher dimension. The energy released from that collision could create an entire universe, perhaps even ours. About 380,000 years after the Big Bang, something magical happened. Before this time, the universe was filled with a dense fog of hot particles. Light could not travel freely. But as the universe expanded and cooled, atoms finally formed. Suddenly, light was able to move across space for the first time. That ancient light still exists today. Scientists detect it as the cosmic microwave background. It is the oldest light in the universe, a faint echo from when the universe was still a newborn. This radiation allows scientists to look back in time, nearly to the beginning itself. Yet even this ancient signal cannot reveal what happened before the Big Bang. There is a wall in the history of the universe, a boundary beyond which our physics cannot yet see. At extremely small scales, gravity behaves differently. Quantum mechanics dominates reality. Our current theories break down. To truly understand the beginning of the universe, scientists believe we need a new theory called quantum gravity. This theory would combine 2 pillars of modern science: Einstein's theory of general relativity and the strange laws of quantum mechanics. Only then might we finally understand what happened at the very beginning of time. One of the most fascinating ideas in modern cosmology is that the universe may have created itself. Some physicists propose that the total energy of the universe may actually equal 0. Positive energy from matter balanced by negative energy from gravity. If this is true, the universe could emerge naturally from quantum fluctuations. A universe from nothing. Not magic, but physics. This possibility suggests that universes may constantly appear and disappear within the fabric of reality. Our universe may simply be one successful fluctuation. Now pause for a moment and consider something extraordinary. Every atom in your body was forged inside ancient stars. Those stars formed billions of years after the Big Bang. The oxygen you breathe, the carbon in your cells, the calcium in your bones, all were created in cosmic furnaces scattered across the universe. You are not separate from the universe. You are literally made of it. And somehow, after billions of years of cosmic evolution, the universe became conscious enough to ask questions about its own origin. Through us, despite our greatest telescopes, our most powerful particle accelerators, and the brilliance of modern physics, we still do not know what existed before the Big Bang. Perhaps there was nothing. Perhaps there were infinite universes. Perhaps time itself is an illusion. Or perhaps the answer lies in a theory we have not yet discovered. But the search continues, and every new discovery brings us closer to understanding the moment when everything began. Until then, the question remains one of the most profound mysteries ever asked by humanity. What was there before the beginning of the universe? And somewhere in the future, humanity may finally find the answer. You know that feeling when the answer makes sense, but somehow it makes the mystery even bigger? When you finally understand how something works, and instead of shrinking your curiosity, it stretches it, quietly, almost imperceptibly. There's a certain kind of person who doesn't feel satisfied with surface explanations. Not because they're trying to be difficult, not because they want complexity for its own sake, but because something in them can sense when there's another layer beneath what's being said. And sometimes that trait gets misunderstood. Curiosity at that scale can be labeled as overthinking, or impractical, or too philosophical, especially when the question is something like, how do scientists know the distance of the universe? It sounds abstract, distant from everyday life. But the instinct behind it isn't abstract at all. It's the instinct to locate yourself, to understand the scale of the room you're standing in, even if that room is 93 billion light years wide. When scientists talk about measuring cosmic distance, they often describe something called the cosmic distance ladder. It's a series of methods layered on top of each other. One technique works for nearby stars. Another works for nearby galaxies. Another reaches deeper still. Each rung depends on the reliability of the one below it. There's something deeply human about that structure. We rarely leap straight to ultimate truths. We build upward from what we can confirm. The first rung involves parallax. If you hold your thumb out and close one eye, then switch eyes, your thumb appears to shift against the background. That shift is parallax. Your brain uses it constantly to judge distance. Astronomers do the same thing with nearby stars. As Earth orbits the Sun, the position of a nearby star shifts slightly against the more distant background stars. That tiny angle, almost unimaginably small, reveals how far away it is. It's subtle. It requires patience, precision, but it works. And psychologically, that's how your mind often recalibrates perspective. You move, your environment shifts, and through that shift, you realize how close or far something truly is. Distance becomes visible through motion. For stars too far away for parallax, scientists move up the ladder. They use Cepheid variable stars, those rhythmic pulsing lights first studied in detail by Henrietta Swan Leavitt. Their predictable relationship between brightness and pulse rate allows astronomers to measure distances far beyond our immediate stellar neighborhood. Then come Type Ia supernova, exploding stars with nearly identical intrinsic brightness. These cosmic explosions act like lighthouses in the dark. By comparing how bright they appear from Earth to how bright they are known to be, scientists can calculate staggering distances. And when Edwin Hubble observed that distant galaxies were red-shifted, their light stretched toward longer wavelengths, he uncovered evidence that the universe itself is expanding. The farther a galaxy is, the faster it appears to be moving away from us. That relationship, now known as Hubble's law, allows scientists to estimate distances on scales that feel almost ungraspable. But here's where it becomes less about astronomy and more about you. Because every one of these methods depends on trust and patterns. The human brain is wired to detect patterns. The visual cortex identifies shapes and movement. The auditory cortex identifies rhythm. The prefrontal cortex searches for consistency across time. We are constantly building internal models of the world, predicting what should happen next. When those predictions hold, trust builds. When they break, curiosity intensifies. Science is not separate from this process. It's a refined extension of it. When astronomers observe that brightness and pulse rate correlate in Cepheid stars, they're doing what your brain does when it learns that a certain tone of voice predicts a certain mood. When they notice redshift increasing with distance, they're mapping a consistent relationship. Just like you map emotional distance through behavioral change. The scale is different. The mechanism is familiar. There's another layer most explanations skip. When we say the observable universe is about 93 billion light-years across, we're not claiming to see its edge. We're describing the limit of what light has had time to reach us since the beginning of cosmic expansion. The universe is about 13.8 billion years old. But because space itself has expanded during that time, the most distant light we can observe today originated from regions that are now far beyond 13.8 billion light-years away. Distance and time are woven together. This idea can feel destabilizing at first. It challenges the way we intuitively think about space. But your brain is already comfortable with temporal distance in a different form. When you remember childhood, you're not accessing it directly. You're accessing stored neural patterns. The event is long gone. The memory is what remains, light from the past, still traveling within your neural circuits. You never experience the present in isolation. You experience the delayed echo of it. In that sense, looking at distant galaxies is not so different from introspection. You are observing something that has already unfolded. And here's a quiet paradox. The more precisely we measure cosmic distance, the more we discover components we cannot directly see. Dark matter does not emit light. Dark energy does not behave in ways that are easily visualized. Yet their effects are measurable. Galaxies rotate too quickly for visible matter alone to account for. The expansion of the universe accelerates in ways that require an unseen driver. We infer their existence from patterns. Just as in psychology, we infer unseen processes from behavior. You don't see your own neurotransmitters adjusting. You don't watch cortisol levels rise in real time, but you feel the consequences. You observe changes in energy, focus, mood. The unseen becomes real through its impact. There's something humbling in that. It reminds us that knowledge is not the same as direct perception. It's a careful construction built from evidence, consistency, and refinement. And maybe that's part of why questions about the universe resonate so deeply with certain minds. If you grew up in an environment where certainty felt unstable, your nervous system may have adapted by seeking reliable patterns. The brain craves predictability. It feels safer when cause and effect make sense. Cosmology offers something rare, a vast and personal order, equations that describe expansion, rhythms that describe stellar life cycles. Even chaos follows statistical laws. For some people, that scale of order is regulating. It provides a sense of groundedness that smaller systems sometimes fail to offer. But it's important to say this clearly. Being drawn to cosmic questions is not superior to being grounded in immediate reality. It is not more enlightened. It is not more profound. It's simply one way the mind organizes meaning. Some people orient toward intimacy and relationships, some toward tangible creation, some toward ideas that stretch across billions of years. Different nervous systems find stability in different anchors. And here's the counterintuitive layer. Understanding the vastness of the universe can make you feel both insignificant and deeply connected at the same time. Neuroscientific studies on awe show that when people contemplate immense scales, like mountains or galaxies, activity decreases in brain regions associated with self-focus. The sense of me softens. For some, that feels like loss. For others, it feels like relief. If you've ever felt calm under a star-filled sky, it might not be because you solved anything. It might be because the pressure of self-importance temporarily dissolved. The universe didn't shrink you. It redistributed you. And yet there is a quiet cost to living with this awareness. Once you understand that the light from a galaxy has traveled billions of years to reach you, everyday frustrations can feel strangely small, but also strangely fragile. The awareness of impermanence becomes sharper. Civilizations rise and fall in cosmic seconds. That perspective can bring clarity. It can also bring a subtle loneliness, because not everyone wants to think at that scale. And that's okay. Different minds require different focal lengths. What matters is recognizing that your fascination with cosmic distance is not random. It reflects a cognitive style, a nervous system that is comfortable with abstraction, a mind that tolerates uncertainty long enough to build models instead of immediate answers. You are not broken for wondering how we know these things. You are not naive for feeling both amazed and unsettled by the numbers. The story of how scientists measure the universe is not a story of domination. It's a story of patience, of collaboration across generations, of refining tools and correcting errors, of admitting when measurements conflict and investigating further. Even now, astronomers debate the exact value of the universe's expansion rate. The Hubble tension suggests that different measurement methods yield slightly different results. The uncertainty is not failure. It's part of the process. Knowledge evolves, just like you do. There may have been times in your life when you felt far from who you used to be, when growth felt like expansion, exciting but disorienting. You measured the distance between past and present by noticing shifts in belief, identity, perspective. That internal expansion mirrors the cosmos more than you might expect. Space stretches, galaxies drift, light travels, and here you are, a configuration of atoms forged in ancient stars, asking how far it all goes. That question alone says something meaningful. It says your mind is willing to sit with vastness. It says you're capable of holding both uncertainty and structure at the same time. And that capacity has value. Not because it makes you special, but because it reflects a depth of perception that often goes unspoken. The next time you hear that the universe is 93 billion light years across, you don't have to treat it as a cold statistic. You can recognize it as the result of human beings paying attention to faint light for generations. You can recognize it as a testament to pattern-seeking minds not so different from yours. And if this way of looking at distance feels strangely intimate, there's more beneath it. There are deeper layers to why certain questions feel like they belong to you. Why scale matters to you. Why vastness feels both calming and unsettling. If this resonates, that exploration can continue. There are still constellations inside your own thinking that haven't been mapped yet. You know that feeling when you look up at the night sky and something inside you goes quiet? Not because you understand what you're seeing, but because you don't. There's a particular kind of mind that doesn't just glance at the stars and move on. It lingers. It drifts into questions that feel almost too large to hold. How far does this go? Where does it end? How could anyone possibly know? And sometimes when you ask those questions out loud, people smile politely, or they shrug, or they say it's just science, as if curiosity about the edge of existence is a phase you're meant to grow out of. But it isn't. That impulse to wonder about distance on a cosmic scale isn't childish. It isn't impractical. It's a pattern, a very human one, and it tells us something important about how your mind works. Because when you ask how scientists know the distance of the universe, you're not just asking for numbers. You're asking something deeper. How do we measure what we can't touch? How do we know something that seems impossibly far away? There's more going on in that question than people realize. Most explanations start with telescopes and formulas. They talk about light years and redshift and expansion, and those things matter, but they often skip the part that makes this story feel personal. The truth is, the way scientists measure the distance of the universe mirrors the way the human brain learns to measure anything unknown. It starts with comparison. Your brain is a pattern-detecting machine. Long before we had observatories, your nervous system evolved to estimate distance for survival. How far is that tree? How quickly is that animal approaching? Can I reach that branch? Neuroscience shows that your brain doesn't perceive distance directly. It infers it. It uses cue size, brightness, movement, contrast. It compares what it sees to what it already knows. And that's exactly how scientists began measuring the cosmos. They didn't jump straight to the edge of the universe. They started with something closer, something familiar. In the 20th century, astronomers like Henrietta Swan Leavitt studied a specific type of star known as Cepheid variables. These stars pulse. They brighten and dim in a steady rhythm. Leavitt discovered something subtle but revolutionary. The brighter the star truly is, the slower it pulses. That relationship changed everything. Because if you know how bright a star actually is, and you see how bright it appears from Earth, you can calculate how far away it must be. Light fades with distance. It spreads out. The dimmer it looks compared to its true brightness, the farther it is. It's not so different from hearing a voice in the dark. You can't see the person, but you can sense whether they're across the room or down the hallway by how faint they sound. The universe speaks in light, and scientists learned to listen. Later, astronomers like Edwin Hubble noticed something even stranger. When he studied distant galaxies at the Mount Wilson Observatory, he found that their light was stretched toward the red end of the spectrum. This redshift wasn't random. The farther away a galaxy was, the more its light was shifted. That stretching happens because the universe itself is expanding. Space isn't just holding galaxies. It's growing between them. As light travels through that expanding space, its wavelength stretches too. So by measuring how red the light is, scientists can estimate how fast a galaxy is moving away. And from that speed, they can estimate its distance. Again, it's inference, pattern, relationship. And if you notice, this is the same way your mind handles emotional distance. You rarely measure how close you are to someone directly. You look at signals, tone of voice, response time, body language, the subtle stretching or shrinking of connection. Your brain reads shifts and translates them into meaning. Distance, whether cosmic or emotional, is something we learn to sense through change. As measurements improved, scientists began using even more powerful standard candles, supernova explosions that shine with predictable brightness. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have allowed astronomers to see light that has been traveling for more than 13 billion years. That number feels abstract, but think about what it means. When you look at a galaxy 13 billion light-years away, you are not seeing it as it is. You are seeing it as it was. The light left before Earth even formed, before there were oceans, before there was oxygen in the atmosphere. You are looking into the past. And here's where the psychological layer deepens. Your brain also works in delayed light. Neuroscience shows that your conscious awareness lags slightly behind reality. By the time you register a sound or a sight, milliseconds have already passed. You are always experiencing a slightly delayed version of the world. In a sense, you never see anything exactly as it is. You see what has already happened. The universe operates the same way. When astronomers measure distance, they are measuring time. Because light takes time to travel, distance and time become intertwined. The observable universe is about 93 billion light-years across. That doesn't mean it's 93 billion years old. It means that due to expansion, the space between us and those ancient photons has stretched dramatically over time. There's something almost poetic in that. We measure the size of existence not by reaching it, but by waiting for it. And maybe this is why the question lingers in you. Because on some level, you understand that knowing the distance of the universe isn't about certainty. It's about humility. Behavioral science suggests that humans are uncomfortable with uncertainty. The unknown can activate the amygdala, the brain's threat detector. Ambiguity can feel destabilizing. Yet some people lean toward it instead of away from it. They find a strange calm in vastness. Research on awe shows that when we experience something immense, like a star-filled sky, the brain quiets its self-referential chatter. The default mode network, responsible for constant self-evaluation, softens. You feel smaller, but not in a diminished way, in a relieved way. When scientists measure cosmic distance, they're not trying to conquer the universe. They're trying to understand our place inside it. And that desire is deeply human. It often begins in childhood. Maybe you were the kind of child who lay on rooftops or stared at a car windows at night. Maybe you asked questions that felt too big for the room. Children are natural cosmologists. Their nervous systems are still mapping the edges of reality. Over time, some environments encourage that curiosity. Others subtly narrow it. Practical concerns take over. Schedules replace wonder. But the pattern remains. The mind that asks how far the universe goes is often the same mind that asks how far meaning goes, how far love extends, how far consciousness reaches. Curiosity about cosmic distance can be a survival strategy of its own. When life feels confined by expectations, by routine, by limitations, the mind expands outward. It searches for scale. It recalibrates itself against something larger. This isn't escapism. It's regulation. Your nervous system sometimes needs vastness to feel stable. And it's important to say this clearly. Being drawn to these questions isn't better than being drawn to practical ones. Different minds orient toward different anchors. Some people feel grounded by the immediate and tangible. Others feel grounded by the abstract and infinite. Neither is more evolved. Neither is more correct. They're just different ways of mapping reality. There's also a quiet paradox in all of this. The more precisely we measure the universe, the more we discover how much we don't know. Dark matter, dark energy, invisible components making up most of existence. The equations that describe expansion don't fully explain its cause. Even the exact value of the universe's expansion rate is still debated. The deeper the measurement, the wider the mystery. That might sound unsettling, but it carries a hidden strength. Science doesn't eliminate wonder. It refines it. Knowing how scientists measure distance doesn't shrink the night sky. It makes it more intimate. The photons entering your eyes traveled billions of years just to reach you. The atoms in your body were forged in ancient stars. Distance doesn't separate you from the universe. It connects you to it. You are, in a literal sense, part of the same expanding story you're trying to measure. If you've ever felt small under the stars, that feeling isn't weakness. It's perspective recalibrating itself. It's your brain adjusting scale. And if you've ever felt a quiet comfort in the thought that the universe is vast beyond comprehension, that too makes sense. Vastness can hold what feels overwhelming. It reminds you that not everything rests on your shoulders. You're not broken for asking how we know these distances. You're not naive for being unsettled by infinity. Your mind is doing what it evolved to do, seeking patterns, building bridges between the known and the unknown, translating light into meaning. And perhaps the most beautiful part of this story is that measuring the universe required collaboration across generations. One person observed a pattern. Another refined it. Another built a better instrument. Knowledge stretched outward, slowly like space itself. The distance of the universe wasn't discovered in a single breakthrough. It unfolded. In the same way, your understanding of yourself unfolds. There are parts of you that once felt unreachable, emotions that seemed too distant to name, patterns that only became clear in hindsight. Over time, with patience, the light from those experiences reached you. You measured your own internal universe the same way astronomers measure galaxies, by noticing shifts, brightness, red shifts of feeling. It's easy to assume that science is cold and detached, but at its core, it's an expression of longing, a disciplined form of curiosity, a way of saying we want to know where we are. And that question, where are we, is the same one that lives quietly in many of us. So when you look up and wonder how anyone could possibly measure something so immense, remember this: we didn't measure it by overpowering it. We measured it by paying attention, by noticing patterns in light, by trusting that faint signals carried information. That's something your own mind does every day. If this way of seeing the universe feels strangely personal, there's a reason for that. The outer cosmos and the inner one are not separate pursuits. They're reflections of the same instinct to find orientation in vastness. And there's more to explore about that instinct. More about why some minds seek infinity while others seek immediacy. More about what that says about how you're wired. If this resonated, that exploration doesn't have to end here.